All right, we're back for day number 2 of section 2.1, tangent lines and the derivatives. Here we have a square root, which is going to be a little bit more challenging. So I will go ahead and start out with just a simple drawing. All right, we've got the point x comma y. Of course, y is radical 6x plus 1. And then, moving a short distance to the right, we have x plus h, comma, and then the x plus h gets plugged into here and distributed to get this. Of course, the line that I want is the tan line, but I can't get the tan line because it only goes through one point and I can't find its slope. So I'll use the secant line, as I always do. And if I do y2 minus y1 over x2 minus x1, I end up with this. And of course, I really can't do much with that. So I have to multiply numerator and denominator by the conjugate of the numerator. So here goes. I'm not going to bother doing this distributive property in the denominator. I will, though, FOIL the numerator. And when I do, I'm simply going to get 6x plus 6h plus 1 minus the quantity 6x plus 1. Those two steps right there. The other two steps are just going to simply add up to 0. They're going to cancel because one's positive, one's negative. Of course, what's going to happen now is when you distribute this through, you'll have minus 6x minus 1. Let me go ahead and just rewrite that. And again, only the h terms survive. Everything else will have something to cancel with, and you can plainly see that that's happening here. So we're simply left with 6h in the numerator. Now we can cancel legally with this h sitting in the denominator, leaving us with simply 6 over those two square roots added together. All right, as you can see, I'm running out of room a little bit, so I'm going to try to clear up some space. Of course, we don't want the slope of the secant line. We want the slope of the tan line, the tangent line. And as we've seen, the slope of the tangent line is the limit as h approaches 0 of the slope of the secant line. Okay, if h approaches 0, that means that this 6h will be 6 times 0, so it's gone, leaving us with 6 over 6x plus 1 and another 6x plus 1, both in square roots added together. That'll be 6 over 2 of those radical 6x plus 1s. Obviously, the 6 and 2 can cancel and reduce down to a 3 and a 1. And that is the slope of the tan line. That is the derivative. All right, let's finally start answering some questions. Part A, we want the slope of the curve, that's the derivative we just found, at the indicated point, which is at x equals 4. So we put the 4 down in here. That's going to be 3 over the square root of 25. That'll be 3/5. All right, we need the equation of the tan line and the normal line, and then we'll graph all three. Well, we know that the slope is 3/5. So that's going to be the slope of the tan line. I know that the normal line then would have an opposite reciprocal slope of negative 5/3, since they have to be perpendicular. I also know that both of them go through the point x equals 4 comma something, so x will have the minus 4 in it. And finally, 4 what? Well, again, we've already seen if you plug the 4 in, you're going to get radical 25, which is 5. And there we have all three answers, parts A, B, and C, and we'll draw a graph to make sure that we're right for part D. Okay, I'm on green globs. On green globs, square root is SQR, so that's the square root of 6x plus 1. Go ahead and graph that. Typical square root curve. The important part is, does it go through the point 4, 5? And yes, it does. Okay, I've typed in my tan line equation. As you can see, it's perfect. And so is the normal line right here. All right, we've successfully done number 3, an example with the square root in it. In number 4, instead, we're going to take the square root out, and we're going to introduce a fraction. I think I'll do this one without that little drawing that I make. That's optional. If you feel comfortable still making that, that's fine. I'm going to head right for the slope of the secant line. I'm sure you've noticed by now we'll always have an h in the denominator. That's never going to change. The numerator will be y2 minus y1. y2, if you plug in x plus h into here, you're simply going to get 3 over x plus h plus 2. So that's y2 minus y1, which is simply the function. And you have that. Really, the only thing we can do here is to get a common denominator, so we will. I'm going to multiply the first fraction's numerator and denominator by a blue x plus 2. In the second fraction, we'll get the trinomial, both top and bottom. Just for good measure, I'm going to make this h an h over 1. And since we are dividing by a fraction now, I'm going to simply multiply by the reciprocal. So instead of divided by h over 1, I'll have a times 1 over h off to the right. That makes this not look quite so imposing. It also gives me a little bit more working space, which is always nice. Let's see what we have here. As you can see, we have the common denominator now, and I wrote it down here just one time. In the numerator, we're going to have 3x plus 6, and treating this as a negative 3 and sending it through, making these all negatives or minus. I'll have minus 3x, minus 3h, minus 6. Again, only the parts with the h's survive. Everything else, the 6, the negative 6 cancel, the positive and negative 3x's cancel, and we're simply left with a numerator of negative 3h. And now I can cancel the h's legally because the addition and subtractions are gone. When I cancel those out, I'm going to end up with simply a negative 3 up top. All right, so that's the slope of my secant line. And now I want to make it the tan line, so I'm going to take the limit of this thing as h approaches 0. And of course, if h approaches 0, this becomes a 0 in the middle, and you get a pair of x plus 2's being multiplied together. So the derivative is negative 3 over x plus 2 quantity squared. There we go. All right, let's answer some questions. Find the slope of the curve at the indicated point. This time x is negative 5. So dropping a negative 5 in here would give us negative 3 over negative 3 squared. So that'd be negative 3/9, which of course is negative 1/3. All right, so that's part A. All right, we'll get the tan line, the normal line, and then I'll graph all three. Okay, we know that we're at x equals negative 5. So that's going to be an x plus 5 in both cases. If we take the x equals negative 5 and plug it into the original equation, we're going to have 3 over negative 3, which will be negative 1. So those will be y plus 1s. And finally, we'll take the derivative, the negative 1/3 slope, and plug it into the tan line. Which means, of course, the normal line will have a slope of positive 3 over 1. All right, there's parts A, B, and C all completed. And I'll prove that we're correct by graphing all three and showing, hopefully, a great result here. All right, here we are in green globs. We've got the 3 over the x plus 2. Notice the parentheses in the denominator, which is mandatory. And it's going to be a hyperbolic graph. You can expect that there was going to be a vertical asymptote at x equals negative 2 because it's not in the domain, sure enough. Also, y equals 0, the x-axis is a horizontal asymptote. We know those things from pre-calc. All right, now I want to go ahead and throw the tan line in. Of course, the point that we went through, you may remember, was the point negative 5, negative 1, which thankfully is on our graph. It better be. Okay, here's the tangent line. That's fantastic. And the normal line. That's it for example number 4. All right, at this point, we're going to start to see the power of calculus. Number 5, it says, at what point is the tangent line, or the tangent to f of x, horizontal? Well, I know that this graph is an upside down parabola. It's a downward opening parabola. And if the tangent is horizontal, that means that the slope is 0, which means I'm right here. And if you've ever wondered how a calculator is able to figure out a max or a min, it takes a derivative and sets the derivative equal to 0, which is the slope of the tan line. So this problem is really asking us, hey, take a derivative, set it equal to 0, and solve. That's really what it's saying, even though it's not saying it. So again, we'll get the slope of the secant line first. That's going to be this rather ugly y2 minus y1 over x2 minus x1, which of course is going to be x plus h minus x. That's just going to be h. I have a feeling this fraction bar is going to need to be a little longer. Let's just take the whole board up. All right, y2 minus y1. Let's go for y2 first. This is going to be interesting. We have a 2 plus 3x plus 3h. And I know what x plus h squared is, but there's a minus in front of it, so it's going to change all the signs to negatives or subtractions in front. So that's going to be minus x squared minus 2xh minus h squared. Okay, so that whole thing is y2. Now, since I'm subtracting off y1, which is this whole thing, since I'm subtracting that trinomial, I'm going to, in my mind, distribute the minus through, and I'm just going to change all the signs on the fly. So I'm going to write minus 2 minus 3x plus x squared. That should save me a little bit of writing. And as always, if you don't have an h, you're going down. Only those blue items in the boxes should survive. Let's make sure everything else does cancel. 2 and negative 2 are gone. Here's a negative x squared, positive x squared, and the minus 3x and the plus 3x. Yep, sure enough. All right, since everything in the numerator has an h can be factored out because everybody has one. So I will do that. That's going to leave me with just a 3 minus 2x minus h, because it was h squared, now it's just h. Speaking of h, that's what the denominator is. And now the h's can cancel each other out. So we have the slope of the secant line. We want the slope of the tan line, which of course in this case should be 0. So we need the h, we need this distance right here to shrink so that the secant line actually becomes the tan line. So as always, the slope of the tangent line is the limit as h approaches 0 of the secant slope. Which means if h approaches 0, obviously that's gone. And the derivative will simply be 3 minus 2x. All right, again, you want your tangent slope to be 0. So I will take this out, put a 0 in instead, and solve a very easy algebra 1 equation. 3 minus 2x equals 0. When you solve that, you're going to get x is 3/2 or 1.5. Now my directions don't say, hey, at what x value is the tangent horizontal. It says at what point? And points have x and y coordinates, so don't bail out early. You did all the hard stuff already. 1.5 comma what? Well, simply take the 1.5 and plug it back into the original. I'll try to do this mentally. We have 2 plus 3 times 1.5. That'll be 4.5. Minus 1.5 squared. That's 2.25. So we have 6.50. I think of money. $6.50 minus 2 1/4. That's going to leave me with $4.25. That's 4.25. And so the point 1.5 comma 4.25 would be the vertex or the maximum. And that's exactly what your graphing calculator does when we plug in an equation and we hit second calc maximum. In fact, we're going to do that right now to check our answer of 1.5 comma 4.25. So I'll go ahead and I'll put the original parabola in. All right, there's the equation. Let's graph it. I'll hit zoom standard just because I don't know where I've been here. There's our parabola. Boy, that sure does look good. That looks like it is topping off at 1.5. Let's check it out. Second calc maximum. And unbeknownst to normal calculator users, what this does right here when I hit enter is it's going to take the derivative of this equation, set it equal to 0, and spit out an answer. Okay, left bound, sure, that looks good. Right bound, I don't know if you know this or not, but since you don't have to like go tap, 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 and keep moving the bug. If you think it's 1.5, just pick a number on the other side. How about 3? That just puts you right over there, so enter. There it is. The maximum is perfectly 1.5. Whoa. Guess what? The current score of the game is humans 1, machines 0. The real answer is not 1.4999966. That's a mistake. Your calculator makes mistakes? Yeah, it's just a machine. It doesn't have a brain. The real answer is exactly 1.5. Now, Texas Instruments is very aware of this. By the way, there's our 4.25 at the end. If I went ahead and I went second calc value, and I typed a 1.5 directly in, you can see that it's going to put me right at the top at 1.5, 4.25. Texas Instruments is not the only calculator that has this issue. Casio, Hewlett-Packard, all the other ones, same thing. Whoever can figure out why this error occurs is eventually going to be very rich. No one's been able to do it yet. Maybe when your kids have the TI, 230s, it'll work perfectly. But interesting. All right, so that's your maximum. That's where the derivative or the slope of the tan line is 0. That's what the calculator does behind the scenes. Takes a derivative, sets it equal to 0, and puts a blinking cursor on that location. That's the algorithm. Cool.